Good evening, good morning, everyone. I'm Mark Sargent. I'm the EC Science Program Manager, and in this third Game Changer seminar of the year, I'm delighted that we can welcome Ingrid Mann from the Arctic University of Norway in Tromsø. Ingrid Mann, our guest today, is Professor for Space Physics in Tromsø. And in her CV, which you may have, or the short biography, which you may have seen in the newsletter, there's the mention of small solar system objects, which are of distinct interest to Ingrid. And it can get arbitrarily small almost with Ingrid, because that includes dust as well, I guess, not really objects, but particles, of course. So yeah, she has very broad interests, as becomes clear when you look at her curriculum and her preferred activities. So yeah, plasma, dusty plasmas in space, physics of the heliosphere, ionosphere, interstellar medium, linking various scales clearly also. And of course, today we'll hear a lot about what all the objects are that contribute to this dust budget as well. So Ingrid clearly also uses lots of different observations and techniques to address these questions. She uses models, she does remote observations, spacecraft, sending them far away and receiving the data, but also space instruments on rockets. So we're really looking forward to a large panorama, Ingrid. Maybe just a few words on where you started your academic pathway. For people on the call who were not aware, Ingrid started out with a diploma and a doctorate at the Ruhr-Universität Bochum in Germany, and then worked at various stations in Europe, but also in Japan and in the US. And since 2016, she holds her current position as professor at the Arctic University of Norway in Tromsø. Very briefly, if you're joining for the first time a seminar in this channel, you can, as a participant, at all points during Ingrid's presentation, leave questions in the chat. We will pick those up at the end, or you can also raise your hand at the end. So Ingrid, thanks very much for joining us today. I'll hand it over to you, and we're very much looking forward to your presentation.
Thank you, Mark. Hello also from my side, and thank you for joining this seminar. And I'm very glad that I have the opportunity to give this seminar here, because actually there are many works that I mentioned that have been discussed in ISI teams, in ISI workshops, and the ISI opportunity was very central for some of the work that I present today. This is just the overview of my presentation today, and I would like to start with an introduction and a motivation why we should study dust in the inner heliosphere. And when I discussed with Mark before the presentation started, we talked already about the fact that he is working on dust in other galaxies. And I think the advantage we have in the solar system is that we are simply very close, and that we can see and study processes that otherwise are only seen, let's say, theoretically. First, to compare on the scale of astronomy, the dust in the solar system forms a disk like the circumstellar debris disk that we nowadays observe around other stars. Here on the left, we see the dust disk around Beta Pictoris. The heliosphere on the other side is the region around the sun that is filled with solar wind plasma, and it shields us from the local interstellar medium. And here on the right-hand side, we see an illustration of the interstellar medium that the sun traverses, and through the interaction between the interstellar medium and the solar wind plasma, the heliosphere builds up. And when we talk about dust in the inner heliosphere, it's also important to note that a huge majority of the dust in the solar system is in the outer solar system. And in a recent work, Andrew Popper gave the estimate that only about 1% of the dust is within about 5 astronomical units from the sun. And this inner part includes, of course, or overlaps with the heliosphere. And on the other hand, it's only 1%, but it's the portion that is best studied. Astronomers observe the solar system dust cloud in the zodiacal light. This is the faint band brightness, or the band of brightness that we see here along the yellow line. And this is a photograph of the night sky taken with a fisheye camera. And as the zodiacal light denotes those particles, as the zodiacal cloud, we denote those particles that generate the zodiacal light by light scattering and thermal emission, but it's also loosely used for the entire solar system dust cloud. So why do we study dust in the solar system? As said already, we can use this as an example for processes that occur in planetary debris disks. Another point is that cosmic dust that reaches Earth influences processes in the upper atmosphere, and that in general, the dust input plays a role for habitability of planets. And some of the impacts of cosmic dust onto Earth we observe as the entry generates meteors, as we see here on the left-hand side. The dust in the solar system finally also provides us the opportunity to study it directly in the laboratory if we manage to collect it. And here on the right-hand side, we see an electron microscope image of such a collected interplanetary dust particle. This was collected in the upper Earth atmosphere. And as you probably know, collections from spacecraft so far are very limited. If we assume that this here on the left is a view of the solar system ecliptic plane, the solar system dust cloud has its highest number density along the ecliptic plane because this is where the parent bodies are located. It's the asteroids and the comets. And the dust is generated through a collision cascade from meteoroids to smaller and smaller dust particles. Because of orbital perturbations, we often cannot trace back the dust trajectories to the parent bodies, and the overall dust cloud seems to be rotational symmetric, and the number density increases towards the sun. There is, in addition, a flux of interstellar dust into the solar system. And it is observed because the sun is moving relative to the local interstellar medium, as I have shown in the beginning. And as a result of the geometry and just by coincidence, the flux of interstellar dust into the solar system is almost parallel to the ecliptic plane, as is indicated in this sketch. Most heliospheric research ignores the dust, and the reason for that is that the effect of the dust onto the plasma is small. I will show one exception, and these are the pickup ions in the solar wind. If we consider the dust near Earth orbit, its mass per volume is comparable to that of the solar wind, but it is contained in massive grains, and therefore, if you would move in a box of about 800 or a cube of about 800 meters, you would just encounter one massive dust grain. The dust is electrically charged because of mainly photoionization in the solar radiation. There is also some charging from the solar wind impact. However, the dust accumulated on the charge accumulated on the dust is very small, and the dust particles are small in comparison to the characteristic scales of the solar wind plasma. Let me now come to the next point. There are a couple of space missions that in the last couple of years have provided new results related to the dust in the inner heliosphere. A lot of progress is being made with white light observations. The SECI instrument is flying on stereo and the WHISPER on Parker Solar Probe. These instruments observe the zodiacal light and its inner extension towards the sun, called the F corona. This figure here shows an image of the inner zodiacal light and F corona looking towards the sun, constructed from stereo observations. This figure summarizes the space missions present in the inner heliosphere that are of interest for these investigations. The stereo and the WIND spacecraft are located near Earth orbit for many years already, and the solar probe and the solar orbiter are located closer to the sun. I mentioned already the white light observations. Aside from that, there is no dedicated dust instrument on these missions. However, these 4 missions carry antenna measurements that are also responding to dust impacts onto the spacecraft. The signals provide only some basic information on the dust impact, but since the entire spacecraft is acting as a collector for these impacts, the number of impacts measured is relatively high, so we have a good statistics of this type of measurements. I said already that we have 2 spacecraft that travel in the inner heliosphere inside 1 AU, and these spacecraft explore regions never reached with spacecraft before. Parker Solar Probe reaches the sun as close as only a few solar radii on the left, and the solar orbiter reaches inside Mercury orbits, and as seen on the right in the lower panel, it moves away from the ecliptic in an inclined orbit, measuring dust and other parameters above and below the ecliptic plane. I mentioned that the dust detections are made with antenna measurements, and this sketches the impact onto the spacecraft body on the left-hand side and the antenna signal on the right-hand side. The dust impact generates free electrons and ions, and depending on the surface potential of the spacecraft itself, the charged particles are either attracted or repelled. And this effect takes a very short time interval, and then after that, there is a relaxation to the normal charging or charge conditions of the spacecraft again. So in other words, the impact process changes for a short amount of time the spacecraft potential, and this is seen in the antenna signal. And I should say that the amplitude of this signal is proportional to the charge production, and the charge production depends on the impact speed as well as on the mass of the particles. These type of dust measurements have been seen since the Voyager, or dust signals have been seen since the Voyager mission, and in recent studies they were used for cluster, Cassini, and MMS by many different groups. And also the physics of the dust impact process and of this detection process was studied in model calculations as well as in laboratory devices, especially the Boulder Dust Accelerator facility. These antenna measurements are typically made to study plasma waves, and distinguishing the dust impact signals can be a challenge. In this context, we have developed a method using machine learning to separate these signals from other signals. This figure shows examples for different antenna signals from which we need to retrieve the dust impacts. In Tromsø, we have applied a machine learning algorithm, and you can see here in the graph the dividing line between detection and non-detection, together with the classification of different events. This plot shows the solar orbiter impacts found with the onboard TDS algorithm in the upper panel, and the CNN machine learning results in the lower panel. The new algorithm could find about 15% more dust impacts, and it leads to a better data statistics. This machine learning tool is published, and it can be in future used also to further dig into the antenna data that have been accumulated by several different instruments. If we talk about dust impacts and measuring dust fluxes, the question of dust trajectories is very important, and I would like to discuss this now. In a good approximation, the dust equation of motion includes three terms: a term related to the Lorentz force for the dust with a surface charge, Q. It turns out to be important for deflection of dust particles in the solar magnetic field if the ratio of surface charge to mass is sufficiently large. And this is usually the case for small particles, several 10 nanometers and smaller. The particles are in addition influenced by the radiation pressure force that pushes particles away from the sun, and by the gravity that attracts the particles to the sun. And for the larger particles that are seen with the antenna measurements, it's often the balance between radiation pressure and gravity that is important for the entire dynamics. And this is often discussed in terms of the beta ratio of radiation pressure to gravity. So we can roughly distinguish three components with different trajectories. The large particles are predominantly influenced by gravity force. Their orbits are stable over years. The large particles are destroyed by collisions and form smaller particles, or otherwise they slowly drift towards the sun as a result of the Poynting-Robertson effect. And this takes thousands of years. The collision fragments that form near the sun are so small that radiation pressure becomes more important, and those particles that are ejected by radiation pressure force typically leave the inner solar system on timescales of years. Those particles that are even smaller are ejected by electromagnetic forces. I should say that these large particles that are sometimes also denoted as alpha meteoroids to distinguish them from the beta meteoroids, these particles are also the particles that make up the zodiacal light in the F corona. And this image of the inner zodiacal light taken with WISPER on Parker Solar Probe shows the zodiacal light and the inner zodiacal light and the F corona. And there is a very faint white line seen here marked with the blue arrow. And this is a dust trail, a trail of particles that was ejected from asteroid Phaeton, a strange asteroid object, unusual object that has some activity and emits dust particles. And combining these brightness observations with in situ measurements helps, for instance, to understand the activity of this object. In the next step, I would like to compare the results from the different antenna measurements that we have at the moment ongoing. This sketch shows all fluxes, the cumulative flux as a function of the mass of the particles. And we see here symbols for measurements for stereo, solar orbiter, PSP, and wind. One can see that all fluxes are of similar order of magnitude and that the size of the detected particles typically is in the range of several hundred nanometer and larger. And these antenna measurements, with the exception of the stereo, do not include nanoparticles. And here on the left-hand side, you see a different sketch where on the right-hand side we have the previous figure, and then we see towards smaller masses 2 data points of fluxes of nanoparticles detected with the stereo waves instrument in the year 2007 to 2010. I will come back to this later again. So first, let's look at the dust in hyperbolic orbits. Those are ejected by radiation pressure force, and they're often called beta meteoroids. This figure is a sketch of a figure showing different detections of these beta meteoroids summarized in a review paper. And we see the fluxes measured with, on the right-hand side, with stereo, PSP, and solar orbiter, several different data points. All these are made with antenna measurements, with electric field observations. And on the left-hand side, we see the measurements, earlier measurements made with dedicated dust detectors. But we can see that all fluxes are of same order of magnitude, which gives this some reliability. To further investigate these beta meteoroid fluxes, we have used in this work the fact that with the spacecraft is on ingoing and outgoing trajectories, meaning it's going with the flux of hyperbolic orbits dust in hyperbolic dust orbits going outward and against this flux. And from the difference of this ingoing and outgoing flux observations in a work by Samuel Kociczak, he has derived or made a fit of the best possible beta meteoroid flux that could explain the observations. And from that, he could derive an estimate of the most probable value of radiation pressure to gravity that would explain the observations. And this are 3 different estimates depending on where the origin of the flux is, either at 0.05 AU, at 0.1, or at 2 AU. And you see that in all cases, the curve peaks around a beta value of just above 0.5, which is just above the ejection limit for the particles. Such an estimate allows us to go back to light scattering models and calculate the radiation pressure to gravity, as was done here in a work by Hiroshi Kimura when he studied cometary grains. And you see here this beta value as a function of the mass of the particles. The solid line is for a spherical grain of amorphous olivine, and the other points denote models for aggregate particles. But you can see that the beta value that is derived from the solar orbiter data is in a good agreement with such a model of cometary dust grains. What was so far not well investigated or well explained with observations is the impact rates that were observed around perihelia. We see here on the left-hand side perihelion passages at different perihelia for Parker Solar Probe. And you see a double peak here occurring before and after the perihelion passage. On the right-hand side, you see a model where the solid line has such a double peak, but the solid line is assuming perfect circular orbits and orbits that are aligned to the orbital plane of the spacecraft. As soon as we introduce a small radiation pressure force, a small eccentricity, or an inclination of the orbit, this does not work anymore and the peak structure disappears. So the question is, what happens with the fluxes in the very close vicinity of the sun? One possible explanation is that electromagnetic forces may play a role here. On the right-hand side, so these are data points for the PSP, second perihelion passage. The solid lines are model calculations. And on the right-hand side, the solid line gives the cumulative flux of grains larger 100 nanometer. And on the left-hand side, there is a simulation for smaller grains that are in addition also, or that are more strongly influenced also by electromagnetic forces. And in this case, we could find that assuming these electromagnetic forces can lead to a different structure of the flux profile at perihelion passage. That is, of course, only one possible explanation. Other explanations could, for instance, be in the dust sublimation, in collisional destruction, or in other effects not yet understood. Coming to the collisional fragmentation, an important question when studying dust fragmentation is, what is the size distribution of the fragments? And here we see two extreme cases. If we have a distribution described with this inverse power law, we can either have a small exponent, which means that the fragment mass is in the largest grain, or we have an exponent larger than 1, which implies that the fragment mass is in the smallest grain. There were two works that studied in more detail the amplitude profiles of the dust impacts measured with Parker Solar Probe to derive the mass distribution of the impacting particles. And the first is the work by Jamie Saleh and colleagues, where they found for the dust impacts inside 0.15 AU a very steep mass distribution indicated here in this plot on the left-hand side. And then a work done by Samuel Kosticek and myself and other colleagues showed for the distances between 0.15 AU outward a much more shallow exponent of the impact fragments or the impacting masses, which would indicate the fragments or the size distribution at this distances. This seems at the first point of view contradictory, but I don't think it is. I think it indicates that the mass distribution of the particles changes with distance from the sun, and that makes perfect sense because most of the dust is generated by collision of larger particles, and this is naturally changing with distance from the sun. I have mentioned already the nanodust before, and let me now show some results related to nanodust in the inner heliosphere. I mentioned already that stereo A and B have seen nanodust particles in the first years of the mission. And this here shows the impact rates on stereo A and on stereo B. And as you can see, the flux is highly variable. And what is even more surprising, it disappeared after 2010. Here again, you see the flux in comparison to the other fluxes. So it is really at smaller masses. So just to remind you, the small particles are more influenced by the Lorentz force, and in most of the estimates of the dust trajectories influenced by Lorentz force, we assume that the charge of the particles is constant in time. This figure sketches the gyration of a charged particle released near the sun about a magnetic field line. And under certain conditions, the gyrating particle oscillates around the rotating magnetic field line, where the inward directed force is the solar gravity, and outward directed forces are the magnetic mirror force and the centrifugal force. We have shown in several studies that under suitable conditions, this gyration about the field lines can really lead to a trapping of the particles, that they're going back and forth along such a field line and stay trapped for a certain amount of time in the vicinity of the sun. And also we have shown that for other stars. However, as soon as this balance is disturbed, or if the other forces are more important, this trapping stops and the particles are ejected outwards. At the moment, we don't know for sure whether such trapping can cause an accumulation of small particles near the sun. For one, they could not be measured yet, and on the other, it is quite possible that they are destroyed by other effects, for instance, the sublimation. Outside from the trapping zone, the particles that are mainly influenced by radiation pressure force, the particles that are influenced by the electromagnetic force, those are here in blue, are ejected outward, and these two blue lines show the velocity increase from 0.2 AU to 1 AU for grains of about 3 or 10 nanometer size. And the oscillations of the velocity are a result of this gyration motion. The red lines show, for comparison, the beta meteoroids, just simple assumption that particles are launched at 0.2 astronomical or 0.1 astronomical units and are ejected by the radiation pressure. And as I have shown before, the solar orbiter results indicate that the radiation pressure to gravity force ratio is around 0.5, which means that we have this case of the lower line of the beta meteoroid ejection. That means the particles are ejected, but they are not accelerated further and are on a relatively low velocity orbit. On the other hand, as one can see here, the charged nanodust can accelerate it to a relatively high speed. And this also made us believe that the nanodust can cause dust signal or can cause antenna signals on the stereo spacecraft, because with a large impact speed, even a small particle can generate a relatively large amount of free charges when it impacts the spacecraft, and this can cause the antenna signals. And as said before, the antenna signals disappeared after some time, which caused a controversy on whether this data really reflect dust impacts. However, there is a new work which might shed some light on this effect. Here in this work, Poppe and Lee have calculated the flux of particles I'm sorry for this, the flux of particles relative of nanodust trajectories that are ejected by the radiation pressure force. And you can see here that for some reason the slideshow does something automatic here. But what we can see is that the nanodust of sizes 15 to 30 nanometer is highly variable in time, and this could explain the stereo results. And here we have from the Poppe and Lee work the comparison of their model calculation with the stereo B data. I should say that also in a recent result, the time series of dust impacts observed with wind indicate signatures of the sun rotation. So, and I should also say that Poppe and Lee in their work also point out that it's quite possible, if their model is correct, that nanodust fluxes will increase again with a changing solar cycle in the near future. Let's now come to dust interactions in the solar wind and in the solar radiation. The most obvious interaction is the interaction with the solar radiation. Dust particles absorb sunlight and are heated. And as a result of this heating, they reach a high temperature near the sun and they sublimate. And different materials, we have here on the left-hand side a list of different materials and the sublimation zone that is predicted when assuming the heating and the sublimation properties of these materials. I should say that these are also size dependent. For many years, the dust-free zone has not been observed around the sun, but recently the WISPER instrument was able to make a prediction of the dust-free zone. On the lower panel, we see here the brightness model for WISPER data. The red line is the model including F corona and the other components that are typically observed with the instrument. And the upper panel shows the dust profile that was assumed to calculate this brightness. So usually the dust profile is steeply increasing with decreasing distance from the sun. But here in this case, we see that the profile increases to about 20 solar radii, then it is flat for a while, and then it disappears inside 5 solar radii. So this would indicate that the dust depletion happens gradually, and this could mean that we just see the subsequent sublimation of different dust materials one by one. Another dust interaction in the solar wind is that the dust particles are hit by the solar wind, and here is indicated that, for instance, a proton would channel through a dust particle on a distance of about 50 nanometer, and in this also would lose some velocity. This means that large particles are saturated with solar wind particles in their surface layer, and it is predicted that when on these saturated particles more solar wind particles impact, there is a recombination of the solar wind particles. And this is one of the interactions that we have. The solar wind can transfer momentum on the particles. There is a charge exchange of the passing ions, and there can be ion recombination on the surface of grains, and also the sputtering, the sublimation, and any other process of dust destruction that we observe can release particles in or components into the solar wind. And this is relevant for the inner source pickup ions that were discovered with Ulysses. And their formation is either from material, dust material, or through dust interaction. And this has been discussed and studied ever since these ions were discovered. The pickup ions are distinguished from the solar wind because they have a different charge state, typically a low charge state, and because they have a different velocity distribution relative to the solar wind. And this velocity distribution depends on the distance where these ions were formed and brought into the solar wind. There's a very thorough recent study made by the University of New Hampshire group where they explained the inner source pickup ions observed with a SOHO through a combination of 4 interaction paths related to the dust and in the solar wind. And they found a good agreement with the data when assuming the interacting dust as smooth chondritic particles. The upper figure shows the relative importance of the different interactions that they assume, and the lower figure shows the velocity distribution of the ions when they are released from the dust. And this velocity distribution is important for calculating the velocity distribution at the location of the measurement. A different process related to the solar wind is the sputtering, the destruction of dust material just by sputtering. And here is shown in this plot on the left, the sputtering lifetime for grains as a function of the size. And please note that the blue lines denote to the sputtering conditions present during CME. One can see that the sputtering lifetime during CME is much shorter. And the reason for that is indicated here on the right-hand plot, which shows the relative importance of different sputtering yields under different solar wind conditions. And what was found in this study is that during CME, the sputtering from heavy elements plays a significant role and can lead to a large destruction rate, especially for silicate particles, namely destroying them. This may be one of the reasons why the WISPER instrument has seen during a very massive CME a depletion of the F corona brightness. On the right-hand side, the plot shows the excess brightness that was observed during different orbital encounters. And during the encounter 13, the shown excess brightness with relative to a baseline brightness went below the baseline brightness, indicating, as described in this work, that a part of the F corona had disappeared during this encounter. Usually it's only electron components that disappear during the CME. Finally, let's talk about the interstellar dust in the heliosphere. The interstellar dust was discovered in the heliosphere with the Ulysses spacecraft, and the discovery was possible because the Ulysses spacecraft left the ecliptic plane, and therefore the interstellar dust flux could be distinguished from other components. Let's consider the dust trajectories of the interstellar dust. On the upper left figure, one can see trajectories for gravity force being larger than the radiation pressure, and these particles are attracted and collimated behind the sun. The right figure is for particles where radiation pressure is larger. These particles are repelled by the sun, and therefore there is an exclusion zone depending on the radiation pressure to gravity ratio. The lower left panel shows the trajectories of several spacecraft that carried dust instruments, and in comparison to them, the exclusion zones for different radiation pressure forces. And one can see that the Helios spacecraft is in a zone where some of the particles, interstellar particles, if the radiation pressure force is sufficiently high, are already repelled. And here we see the different interstellar gases detected. And you see Cassini, Galileo, Ulysses data, and here the Helios data, where the dust flux is clearly smaller, but it is present and it was observed inside 1 AU. Let's briefly also talk about the dust impacting, or the interstellar dust impacting Earth. This study was made by Peter Strupp and colleagues. The figure on the right shows the flux onto Earth over 2 years. The broad maximum is from the region where the Earth travels against the interstellar dust flux. And the peak that is seen here for a short time is due to the collimation or the focusing of the particles that are mainly influenced by gravity force. The max flux onto Earth is varying over 22 years, in average around a factor of 2. And I'm sorry for this. We see a large variation of the small grains flux, but a very flat profile of the larger grains. And this difference is because the small grains are influenced by electromagnetic forces, but not so the larger grains. In a very similar way, the Stereo A and B spacecraft could detect interstellar dust particles just by the annual variation of the flux, which is due to the observation geometry. And I should say that at 1 AU, continued measurements of the interstellar flux were made with wind and stereo, and there are a number of references here. There is a variation with the solar cycle, but the flux is there. Now the question is, why don't we see the interstellar flux with solar orbiter? And this is illustrated with this figure where we have the solar orbiter flux and the fit with large solar system dust particles in this upper range, and here the estimated expected interstellar dust. And we can see that the expected interstellar dust fluxes are in regions where the solar system dust flux is very high. And our suspicion is that because of this huge difference, basically the interstellar dust flux is hiding here in the data because it is in comparison very small. This brings me to the last point, and this is what's next. A very important aspect to study in the future is to look further into the question of interstellar dust in the heliosphere. This sketch shows the size distribution of interstellar dust from astronomical observations in solid lines, and the red dots are the Ulysses and Galileo data of dust measured in the heliosphere. And these shows the most relevant open question already, and this is, why are the interstellar dust particles seen in the heliosphere so big? What's the reason for this particle size? And other open questions are, of course, what's their composition and what's their flux and the flux variation? Fluxes and flux variation we can in future also measure with antenna measurements. Composition measurements depend on instruments that can measure dust composition, and that requires dedicated dust instruments. The upper panel here shows spectra taken with the Cassini dust instrument, and the lower panel here shows a spectrum that is expected to be measurable with new time of flight mass spectrometry instruments that can be built today. And two of these instruments are going to be launched this year. This is one of them. It's the dust instrument on board the Destiny Plus mission. It's a JAXA mission. The mission is going to fly to the asteroid or object Phaeton, and which is, by the way, also the parent body of the Geminids meteor shower. And it will, on the way, measure dust between about 0.1 and 1.1 astronomical units. A similar mass spectrometry instrument is on board the Interstellar Mapping and Acceleration Probe, which will make measurements from 1 AU to study the interaction between the heliosphere and the local interstellar medium. However, the dust instrument cannot distinguish orbital parameters, so it will be difficult to distinguish impacts from interstellar dust from solar system dust. And hopefully the ongoing observations with antenna instruments on board, for instance, PSP and Solar Orbiter, might help to distinguish these different components. To end, let me show this list of the ongoing and upcoming in situ measurements. I have discussed here wind, stereo, Parker Solar Probe, and Solar Orbiter data. They all will continue observations, and we will have in the near future dedicated dust instruments both on IMAPS and on Destiny Plus. And finally, there will be new measurements with the instrument on board Bepi Colombo. With this, let me end my presentation, and I would like to thank all my colleagues with whom I had the opportunity to discuss this in the last weeks, but also in the last years. And also I should mention that some of this work also goes back to collaborations that started in ISI teams, where I had the opportunity to participate. Many thanks.
Thank you. Thank you, Ingrid. This was very interesting. As I said, a new world for me. I usually measure dust masses of tens or hundreds of millions of solar masses, and you clearly are looking at the individual grains, which is just a fascinating span to think about. Yeah, you can raise your hand or place questions in the chat. We'll get to those that have already been added to the chat in a minute. Ingrid, I wanted to start out by just asking you about that size distribution which you showed close to the end from the Drain et al. Review paper. So there is no sign whatsoever of a cutoff. You know, the data points in red, the large grains, there's no sign whatsoever of that distribution turning over. Did I interpret that correctly?
Yes, this is, however, a little bit an effect of this particular presentation. When you extend this curve further, actually, I should say that these observations motivated many people to look for interstellar meteors, to go to the very large size end. And basically, when going to this large sizes, one could so far show that the amount of interstellar meteors is very small if they are present. So we know that there is a cutoff, but in this particular presentation, it's not very clear. And one point here is that when you go to larger masses for the Ulysses or for dust instruments in general, a limitation is in the size of the instrument, so that just the statistics is getting very bad. But there are data that indicate that the flux goes down again. Let's put it this way.
Okay.
And I should also say that there are also other models of interstellar dust size distributions. Some also suggest the presence of larger particles, but not very many.
Okay, well, let's dive right into the questions that are online. I'll read them out to you, Ingrid. So I'll start with Andrew Lazarevic's question, which I think is a really good one to take first, as it refers to how all this is measured to a certain extent, especially for those of us who are not so familiar with these techniques. So he asks, were the spacecraft involved designed with dust particle physics or geophysics in mind, so affecting how they were built and conceived and maybe equipped, or not?
Yeah, that's a very good question. I forgot to mention that these 4 missions are all heliospheric physics missions, and the dust measurements were not primary science goals. However, in the last 15 years, dust detection with these antenna measurements were more and more often seen. And as a result, at least some of the onboard data algorithms were adjusted. For instance, this TDS algorithm that I mentioned was adjusted to looking for impacts from dust particles. And there's also an opportunity to look more into the data and to study even further the potentially still existing dust impacts there. But it's correct that the antenna measurements themselves were not designed for dust detection.
Okay, and a new instrument coming along is subject of the next question by Richard Frazen. So he asks, do you have any opinion to share about the F corona calibration of the new punch coronagraphs?
Well, I'm not familiar with what type of calibration they are planning to make, so I can't comment directly on that. But the F corona brightness is in general a difficult brightness to analyze, because in the observation of the dust, we do have a signal that is generated from integration along the sightline. And in this sightline integration, the particles at different distances contribute with different scattering angles. That means analyzing the brightness requires assumptions on the scattering properties of the particles. And this is, of course, a difficult task. Yeah.
Right. The very first one which came in at the beginning of your presentation was from James Salmon. So he asks, is the recent interesting suggestion that zodiacal dust may be largely from Mars of any relevance?
Well, there are over the years different estimates on when you look at the zodiacal dust, whether that comes from comets, from asteroids, or from other objects. a direct proof one could only have from observing the direct dust production at a certain object. Indirect proofs we can have from the optical properties or from other particle properties that would indicate a more, for instance, asteroid type origin or a more comet type origin. It's quite possible that, did you really say Mars?
Yes.
Yes, it's quite possible that there are dust particles from Mars, but then still the question would be, where do we leave all the dust released from the asteroids and the comets? And do know that asteroids and that comets, for instance, generate meteor showers. So we know that there are large amounts of meteoroids from comets in the interplanetary medium, and those by collisions generate smaller dust. So we know that there is dust from asteroids and from comets present. So
yeah, I mean, on
other
that
objects
one,
would be
oh,
just
sorry, I
in
didn't want to cut
addition.
you off.
No, fine.
I mean, on that one, you showed, I think around slide 20, the dust trail from an
Yeah.
asteroid. And I was just wondering, so is it feasible to measure composition changes along that trail, actually? I mean, do dust properties change on the timescales that one can see such processes in a tail?
So usually you don't see changes of, well, this is a special case because it's relatively close to the sun. When you have observations of comet trails, you may be able to see a change of the properties along the trail. When you have observations, sorry, what did you ask again?
Yeah, I mean, Mary, this is a silly question of an extragalactic astronomer, but I was just wondering, the asteroid moves, right? And the trail follows. So, I mean, or is left behind. And I mean, presumably, the radiation impinging on the material being left behind, it will have had time to alter things that are further behind the asteroid. It'll have had more time to alter those than something close by. So are those changes measurable?
For debris from asteroids, I would think it's not very likely. Because the changes may not be very strong. However, if you have a comet where you have the ejection of an icy object, then you really see these changes.
Okay. Yeah.
And this is also another aspect I forgot to mention. One point of the Destiny Plus mission is also that through measuring close to the asteroid, there is a chance to measure composition of dust particles, particularly from this object. Okay. This is also a way to study the composition. Yeah.
All right. Well, thanks for addressing that question I had. And there are a few more which came in a couple of minutes ago. So Ratislav Krupor asks, the white light instruments listed for dust detection include stereo H1, stereo high, I beg your pardon, PSP whisper. Could you clarify why solar orbiter high is not considered suitable for this purpose? So stereo high was, I guess, is the question, but solar orbiter high not, as far as I understand.
Sorry, that was from my side. I left that out. That was not on purpose.
Okay.
Yeah.
Andrew Ball asks, will the SUDA dust analyzer on Europa Clipper provide data during cruise on the heliospheric dust populations?
I don't know for right now, but I know it's it's always a fight in the with ESA or NASA to have crew signs. Sometimes it's possible during certain parts of the mission. Um, I'm not sure exactly what's the final answer on that. Yeah.
Ajin Lee asks, have interstellar dust particles been detected on the International Space Station? Is such detection still ongoing?
Um, we have very little information about interstellar dust in the, let's say, in the direct Earth environment. There are some predictions that the interstellar dust can be detected there. There are also some predictions that interstellar dust was directly collected. Whether there is I'm not aware of any definite detection or definite identification as interstellar of any of the space station observations. And the answer could be, well, it's probably there, but we don't know where, or we can't distinguish it from other components.
Okay. And to wrap up, a final one from Richard again. He asks, is light scattered from dust likely to be unpolarized as is usually assumed?
Yeah, that's an interesting question. It's a whole field of studies looking at because when we talk about the zodiacal light, we often talk about the characteristic scattering as a function of the scattering angle. But together with that, there is also a polarization, and the light scattering at these particles goes along with a characteristic polarization. It was studied in detail for cometary dust because there you have a different observation geometry where you know very well the scattering angle. So you have the scattering dust particles are at a certain distance from the light source and therefore at a certain defined scattering angle, and therefore the deriving the polarization is more straightforward. There is also polarization of the zodiacal light, but this is relatively small and it's a little bit more difficult to decompose because, as said before, there are different scattering angles or different particles contributing to the observed brightness, and those particles contribute with different scattering angles. So it's a problem of the line of sight inversion, but there's certainly a characteristic polarization, which also depends on the surface structure and on the composition of the particles.
Okay, well, that's it. You've addressed all questions. Thank you for staying with us for so long. I'll just comment and thank that James, who mentioned the Mars dust before, has actually provided a reference in the chat.
Thank you very much.
Juno results, Stanley 2021. So that closes the loop on the starting point for that question.
Thank you.
So I have just two more things to say. The first one is we'll take an Easter break in April, I believe, from this series. And after that, the next topic will be gold in the universe. So going from dust to atoms, actually, with speaker Stefan Rosvo from Hamburg Observatory. And my second point and final one is thanks to you again, Ingrid, for your talk today. It was a
Thank
pleasure,
you.
and thanks for everyone joining, and see you again in May.
Okay.
Bye-bye.
Bye.